Well, hello students, welcome back to Mathematics Specialist class with me, Mr. Alfie. In this video, we're going to learn about the new chapter about trigonometric. Let's check this video out. Now, we're going to talk about trigonometric identity. Let's say this is a right angle triangle and this angle is beta. So, this side is opposite, this side the adjacent, and this side the hypotenuse. So sine of beta equal to opposite side per hypotenuse, cosine of beta equal to adjacent per hypotenuse, and tan of beta equal to opposite per adjacent. So this is the quadrant of trigonometric. This is the first quadrant, the second quadrant, the third, and the fourth. At the first quadrant, all the trigonometrics are positive. At the second quadrant, only sine and cosine the positive. It is 90 degree till 180 degree. And in the third quadrant, it's only tan and cotangent, the positive. It is more than 180 degree until 270 degree. And in the fourth quadrant, only cosine and secant, the positive. It is more than 170 degree until 360 degree. Example. Given that sine theta equal to 8 per 10, where theta is an obtuse angle. Now, let's say this is the triangle that represents this case. This is the angle of theta. So we know that theta equal to opposite per hypotenuse. So the opposite is 8 and the hypotenuse is 10. By Pythagoras theorem, we know that the adjacent side is equal to 6. So this side equal to 6. So the value of cosine theta equal to negative 6 per 10. Why negative? Because theta is an obtuse angle. So it's 6 per 10. The adjacent per hypotenuse. How about the tangent theta equal to negative 8 per 6? Why negative? It is also because theta is an obtuse angle. It is opposite per adjacent, 8 per 6, the negative. Okay, at the first quadrant, its refer angle equal to the actual angle. At the second, refer angle equal to 180 minus the angle. And the third is reverse angle equal to the angle minus 180. And the fourth quadrant, reference angle equal to 360 minus the angle. Let's say, solve the following equation for the alpha more than equal to 0 or less than equal to 2 phi. We know that phi equal to 180 degree. So 2 phi equal to 360 degree. So we're going to find the value of alpha if sine of alpha equal to 0. So the alpha is actually equal to 0 because sine 0 equal to 0, alpha equal to 180. And alpha equal to 360 degree. How about the value of alpha if cosine alpha equal to half? We know that the value of cosine alpha is positive, and the positive value of cosine is the first quadrant and at the fourth quadrant. The first quadrant, the value of positive a half equal to 60 degree, and at the fourth quadrant, the value of cosine equal to half equal to 300 degree. Why 300 degree? Because the fourth quadrant is reverse angle equal to 360 minus the angle. We choose the angle 60. So 360 minus 60 equal to 300. This is sum of trigonometric identities. Cotangent theta equal to 1 per tangent theta. Cosecant theta equal to 1 per sine theta, secant theta equal to 1 per cos theta. Tan theta equal sine theta per cosine theta, and cotangent theta equal to cosine theta per sine theta. And then there is sine squared theta plus cosine squared theta equal to 1, tan squared theta plus 1 equal to secant squared theta, and 1 plus cotangent theta equal to cosecant theta. So we know that cosine square A plus sine square A equal to 1, which A is the angle. Based on this identity, we can find the formula of cosine square A equal to 1 minus sine square A. You simply just move sine square A to this side. it becomes negative. And then sine square A equal to 1 minus cosine square A. You move cosine square A to this side. And then based on this formula, you can find the value of tan squared theta equal to secant squared A minus 1. And based on this formula, you can find the value of cotangent square A equal to cosecant square A minus 1. Let's jump to example 1 in your book. Prove the identity that tan theta minus sine theta cosine theta equal to sine squared theta tan squared theta. You can prove this identity by the left side to form the right side, or the other way around, from the right side you form the left side. In this example, I'm going to work from the left side to form the right side. Tan theta minus sine theta cosine theta. We know that tan theta is actually sine theta per cosine theta minus sine theta cosine theta. So we make the same denominator is cos theta. So cos theta, this is cos theta, this is still sine theta. And for this, you multiply with cosine theta. So this is cosine square of theta. Now, we simply just factorize this, with become this one. Sine theta equal to 1 minus cosine squared theta, because there is sine here and also there is sine here. So we know that sine per cos multiple with 1 minus cosine squared theta. This is equal to tan, and this is actually equal to sine squared theta. And now you just move it. You will find that sine theta square tan theta square. It is proved equal to this one. In example 2 from your book, prove the identity tan theta cosine theta minus sine cube theta equal to sine theta cosine squared theta. I'm still going to work from the left to form the right. Tan theta cosine theta minus sine cube theta. We know that tan is actually equals to sine per cosine. So sine theta per cosine theta times cosine theta minus sine cube theta. You can dismiss the cos because there's a cos at denominator and there's cos here. So it is only sine theta minus sine cube theta. You can factorize this one because there is sin here and also there is sine here. Sine theta multiple with 1 minus sine squared theta. So we know that 1 minus sine cube theta equal to cosine squared theta. So it is proof. Now, in exercise 9a number 10, we're going to prove that 1 per 1 plus tan squared theta equal to cosine squared theta. We know that 1 plus tan squared theta is actually equal to secant squared theta. So it is equal to 1 per secant theta multiple with 1 per secant theta. We know that 1 per secant theta is actually equal to cos. So it is equal to cos theta multiple with cos theta. Cos theta multiple with cos theta equal to cosine squared theta. So it is proved. Again, I'm working from the left to form the right.